All right, so today we're going to talk about worlds and levels and units. So we've been going through a lot of lower level stuff, and this is kind of the point where we get into real game objects, creating actual game objects that we can do stuff with. And all these concepts are related to that. So worlds to begin with. A world in the Stingray engine is a place or a context in which a number of different kinds of game objects can live. So we saw before in the previous lecture that the world owns a physics world where physics objects live. But there are other objects too that can live in the world. We have units, and a unit is kind of our game object. It's the thing that in other engines is called a game object, maybe, or something else. But that's the main thing that you spawn into the game. So the player is a unit. The room is a unit. You have trees; they are units. Any pickups are units too. So it's a thing that you spawn in the engine, and those units live in a world. So the world is like the coordinate system, the place where all of these things live. The world knows about animations that are playing on these units. So the world is running the animation player, making sure that animations are played. Physics, as I said, the world owns a physics world where the physics live. Particles live in the world, they play at some location in the world. Entities, which I'll talk about more in a future lecture. Entities is kind of our replacement for units going forward. So it's a system that's still under development. But I will talk more about that in the next talk actually. So we'll not talk more about entities today. The vector fields that I talked about in the last lecture, you can have things like wind and stuff like that, and those things also live in the world. The wind blows through a particular world. Decals are spawned in the world, decal projections, and other stuff. Lots of different stuff. All of that is contained in the world. You can have multiple worlds running at the same time. They can sort of coexist. And a typical case where you might want multiple worlds is, for example, you may want to have a main game world where all your main characters are running around and doing stuff. And then maybe you have a separate world for the inventory. So if the user goes into an inventory screen, perhaps you want to show a character in that inventory screen with like gear that you can put on the character. So you need somewhere to put that character and somewhere that you can place these things on him. That character with this inventory on him needs to be somewhere, and the best place to put the character is in a separate world. I used to work on an engine before where we didn't have support for multiple worlds. And then what you did instead is that instead of having a separate world for the inventory, you just made a secret place somewhere in the game world, like 1 kilometer away from your, or you go underground or something. You had a secret room, which was actually the inventory room, and then you teleported the player there to sort of put inventory on the player and then teleport it back to get back into the game. That's not a great solution. It messes with all kinds of system when you want audio and stuff, and so it's better to support multiple worlds. You might want to have a separate world for your menu. If you have like a mini map in the game, you might want to put that in a separate world, so you have that separated from the main world. Another typical case might be loading screen world. Since we can stream in content in the background, you might want to have like an animated loading screen where stuff happens while content is being streamed in, and it makes sense to put that in a separate world so it doesn't interfere with your game world. We also differ a bit from other engines in that these worlds are explicitly updated and rendered from Lua. So in Stingray, Lua has complete control over driving the game loop. In some other engines, it's more your sort of scripting code is more snippet based. You write little pieces of code that you attach to game objects, but the main running of the game happens inside the engine, inside the application loop, and then you will just get call-outs to these little snippets that you have everywhere. There are like advantages and drawbacks of that kind of programming. One advantage is it's a bit easy to get started. You just add behavior. Yeah, that's true, Dan. You can do all of this from using the C API too. The C API supports everything that we have in the Lua API, so all gameplay code can be done through the C API as well. I'm just saying Lua, that's the most common case. But yeah, having little snippets is kind of nice when you get started with experimenting with an engine, because you can just go into a game object, write a little snippet of code, and make that particular game object do something. But with that kind of programming, it's pretty hard to get an overview of the system, of everything that's happening, and you can get a feeling that you don't have a clear picture of where performance goes when it's spread out in little snippets everywhere, and also that you have no real control over the order in which things happen. Like you get callbacks, but what exactly is the order? So we've chosen a system that is more like traditional programming, where the gameplay code, whether it's Lua or C, is actually in control. So the gameplay code is the one that will create worlds, destroy worlds, and also call update on the worlds, which will cause the animations and things that happen in the world to be updated. And the gameplay code can choose to stop updating a particular world. For example, if you're in the inventory world doing stuff with inventory, you may stop updating the game world because you don't want the game to run simultaneously with doing that. So, but the interesting thing here is that this is kind of a general philosophy behind Stingray, that the gameplay code should be in complete control, and it should be more like a regular program with a main loop, a control over the game loop, than little snippets of code, little snippets of callbacks code sort of spread out everywhere. Can have a quick look at what the world looks like. Let's see. So it basically just keeps track of a number of things, and then you can ask it for those things. It keeps track of loaded levels, of units. You can ask it for a particular unit. You can spawn or destroy units. You can spawn entities, ask it for entities, update the world in some various ways. Sometimes you want to split the animation, and animation players, and yeah, lots, particles, all these different kinds of things that the world keeps track of. So the world doesn't do a ton of stuff, it just keeps track of all that other stuff that lives in the world. Units, as I said, unit is our main game object, sort of. And the unit is, again, a kind of container for a bunch of things. So a unit can have a number of meshes that belong to the unit. So those are things that we draw. A unit can have terrains for our terrain system. There can be cameras in a unit. There can be physics actors that belong to a unit. Lights can belong to a unit. Can have an animation state machine that belongs to a unit. Actually, there can only be one animation state machine in a unit. You can have multiple state machines controlling the unit. And some additional unit data. So again, a unit is a container for a bunch of stuff. You set it up using the unit editor tool. So you typically start with some exported file from a DCC tool, typically an FBX file, and that file will specify the meshes and the graph of nodes, the node tree that exists in the unit, and stuff like that. And then in the unit editor, you can sort of add additional things into this, add physics actors and configure lights and so on. As I said earlier, we plan to replace the unit system with an entity system. So if you're familiar with an entity system, that's more like a looser thing. In an entity system, you have an entity, which is kind of an abstract thing, and then you have a number of components that get added to this entity, and each component can do different things. You might have a physics component for physics, a mesh component for a mesh, camera component for a camera, a light component. But the main difference is that this list of components is not fixed as it is in the unit. You can add new components to the system and add those to the entity. So if we look at the unit here, the definition of the unit class, we have a fixed list of the things that a unit can contain. So we have vectors of things like meshes, cameras, light, actors, joints, terrains, movers. So fixed list, and the unit can only contain these fixed things that are like that are predefined in this list. Whereas with the entity, we would actually be able to extend the kind of stuff we can put in with new stuff. So if we look at the functions here, the methods that we expose in the unit, they are typically for manipulating these things, like getting the animation state machine, getting the joints, getting the movers, getting the vehicles, getting all this stuff out of the unit. So the reason we want to move to entities are, first, it's more lightweight by default. Like when we create a unit, it has to have all these vectors. So a lot of them could be empty. Like if we don't have any meshes, that's just an empty vector, and that's just a few bytes of data. But still, there's something there. We always have a scene graph, for instance. Whereas with an entity without any components is really nothing. So we can do really lightweight stuff with the entity system if we want to. But the bigger advantage is that we have this extensible system with kind of a looser coupling. So instead of having with the unit, if we want to add something new to a unit, we don't have a really good way of doing that. There are some tricks that people use to do that. For example, this unit data here, that's essentially JSON data that we can store in a unit. So people can store some special markers in that data, and then they can scan the units for that data and use that to initialize other systems and put units into those systems. But that's not a very nice solution, and it's not super efficient. So really like going to a more looser system. And with the entity system, since we're also moving more and more to a plugin model, the entity system will allow new components to be defined in plugins, so we can sort of extend what game objects can do through plugins. Whereas here, with the unit system, we're pretty locked down in what we can have in the game object. So we're going for a more flexible, less coupled, more extensible, and more plugin-based system, which is where we want to be. That's in general the kind of stuff that we like to have in our engine. Another advantage of the entity system is that we add support for things like inheritance and overrides, or prefabs as it's called in some engines, which we don't really have in the unit system. In the unit system, you can't have units that inherit from other units. So if you want to create multiple varieties of the same unit, you either have to create completely separate units and configure them separately, or a single unit that gets sort of kitted or configured by a Lua script or by a flow graph for that unit. This can be done, but it's a bit more cumbersome than having a proper inheritance and prefab system, and a lot less powerful actually. Yeah, so that's the unit container for stuff like this, and methods for manipulating this stuff. One of the more important parts of the unit is the scene graph. So the scene graph is the tree of nodes within a unit. So it's your typical hierarchy of bones and nodes in a unit. So in a character, that would typically start with the root point, since it's called that since it's at the root of the scene graph. And then that you have hips linked to that, like multiple hips maybe, and then you have neck bones and arm bones and finger bones and so on. And they're all connected to each other, as in the song. So this scene graph is used to represent this hierarchy of nodes and do transforms on this hierarchy, so that when you change the rotation of the shoulder bone, all the bones in the arm get updated with new positions too. So taking care of those hierarchical transforms. Now, an important thing to note is that the scene graph only deals with this node hierarchy inside a single unit. There are some engines that put everything that we have in a world into the same scene graph. So it just becomes one huge scene graph, and then you sort of evaluate that entire graph in order to update the world. We don't really like that model because it tends to create strong couplings between everything in the scene, and it's kind of hard to parallelize, and it's kind of hard to figure out exactly what's going on with these graph updates. So we like this model a lot better, where we just have these small graphs inside one unit. We have one small graph, and then another unit has another small graph, and so on, and they're all separate. If you want to have a hierarchy between units, and there are situations, a lot of situations where you might want that. For example, you might want to put a weapon in the hand of a character. So then you would link the weapon unit to the hand bone sort of the character. But we don't handle that by putting all this stuff into the same graph. Instead, we have a separate mechanism for handling unit linking. So we have and I'll actually talk a bit more about that mechanism later, but there's a separate mechanism that allows us to link one unit to another unit. So these node graphs are only within a unit, and they're pretty small. And another nice thing about them is that they are usually static, because we don't change the linking within a unit. We don't suddenly move the arm bone and link it to the other shoulder or something weird like that, which is also good because it allows us to optimize things because it doesn't change. If we had a scene graph for the entire scene, for the entire world, then we would necessarily have to do a lot of changes to that scene graph. As objects are spawned, they would be linked into the scene graph. If a player picks up a sword, that sword would be linked into that graph, and so on. So then we would have to deal with a mutating graph, which would make some algorithms slower. So I think this is a good approach in general. Another interesting thing that also is a contrast to some other engines. In some engines, what you see is that you have all the objects that can sort of be animated, like meshes and lights and so on, all the objects that have position. They inherit from a common base class, and then like scene graph object, and then those scene graph objects are the things that live in the scene graph and that form the hierarchy of the scene graph. But it's usually a pretty bad design. It leads to pointer chasing and bad cache behavior when you're trying to walk the scene graph, because you're jumping between these different objects. You get a lot of virtual calls, you get instruction cache misses because you have different kinds of objects in the same graph, which is usually a bad thing for caches in general. You want to keep the same kind of objects together, not have different kinds of objects in the same list. So I think that's a bad design, and we don't do it that way. Instead, the scene graph is just a list of nodes. So the scene graph basically only contains local transforms of the nodes, world transforms of the nodes, and links, like what is the parent node of this particular node. And things like meshes and lights, instead of being in the scene graph, they are attached to a particular node in the scene graph. So a mesh knows, for instance, well, I'm attached to node 7 of this scene graph. And as scene graphs are static, it will always be attached to node 7 of the scene graph, which is another nice property of having these static scene graphs. So meshes, lights, and things like that are not themselves nodes. They just reference a particular node, and they get their transform from that node in the scene graph. So as I said, nodes have local transform, world transform, and a parent. And usually when scripts or animations move around something, move around the node, they just move the local position. And then at some point, we do a transform, and we compute the world position from the local position. And we do this in kind of a lazy way, you might say, in that we only do the local to world update once per frame. So we have a particular point in the world update where we do, okay, now let's transform our scene graphs, and then we do the scene graph transform for all objects. So when you change the local position of an object, the world position won't change immediately. So if you change the local position and then ask for the world position, you will still see the old world position. Changing the local position only sets a bit flag in the scene graph that tells us later that we need to do this update and we need to compute the world transform. So there's advantages and disadvantages of this model. The advantage is that even if you change the local position many times, and even if you have a long chain like an arm and you change the local position of every object here in the arm, you only pay the transform cost once for each node. You only ever transform one node once. So it's cheaper in that way. On the other hand, the drawback of this is that the world position of objects will be out of date until we get the update. So there are a lot of scenarios in the engine where you moved one object in the gameplay code, and then you check the position of some other object, the hand, say, you move the shoulder and check the hand, and the hand you won't get the actual position of the hand because we haven't computed the transform yet. And in some cases you can get around this by just thinking about the order in which you check things and stuff like that. But in some scenarios, you're forced to sort of explicitly transforming the scene graph because you need the world position right now. You can't wait for the update. And the most typical thing where this happens is with the camera, because typically you move all the characters in the world and then you do an update to get, and then you want the camera to look at something or follow something, but then you need the world position of that thing in order to move the camera. So you do the world position, compute the world transforms, move the camera, but now you've only moved the local position of the camera. So to get the camera to update its world position, you then need to force an update on the camera and say, oh, now you need to explicitly compute your world position right now. So so there are scenarios where we have a method for that, for saying, oh, actually, don't wait for sort of the world update. Go and compute your world position right now for those scenarios that you need this. So this design I used to think this was like a good design, that it really made sense because yeah, it saves performance. We only do the transforms once and so on. But my thinking now is that this design, this sort of lazy update, actually might not be such a good choice. And my reason for that is that, well, first of all, it's this reason, this sort of thing that, oh, the world position isn't updated yet. That's something that trips up people again and again and again. And I think it's something that really complicates, like having to think about these kind of frame delays is really tricky when you're trying to make a solid system in the gameplay code. And as I'm thinking of it now, we don't really have, I mean, the case where it gets more expensive, so the alternative to this, I should say, is of course to do the transform directly. Like when you set the local position, we do the transform of the entire bone chain so that everything below that node gets the right world position. And so this can be more expensive, but usually our bone chains aren't super long. It's not that common. And this is specific to our engine, since we don't have the scene graph of the entire scene. We only have it within one unit. So it's only ever within one unit that this matters. And the bone chains are usually not super long. Like maybe from the root point to the finger, you have like 10 bones at most. So that's 10 transforms you have to do. So it's something, but it's not super long. And if you think about it, the only time when this becomes more expensive, like if you say that I have my arm here and I have 5 transforms along the arm. If I move the shoulder and do the update immediately, I have to compute 5 transforms. If I did that in the sort of delayed, lazy way, I would move the shoulder, I would still have to update 5 transforms. So it would still cost the same. The case where it becomes more expensive is if I move all the bones along the way, which you typically do in a character animation. Because then I would update this one and transform 5 bones, update this node and transform 4 bones, update this one and do 3 bones, and update this one and do 2 bones, and so on. So then it sort of becomes n squared instead of ordo n, which is becoming pretty expensive. But my thinking these days is that, well, in those scenarios where we have the animation driving a character, then we can sort of do a batch update. So we can have a special function from the animation system that says, well, now I'm going to modify the local bones and don't compute any transforms right now because I'm going to move all of the local bones and compute all of the transforms later. So do this thing as a batch update and compute all the local transforms. And then you will have proper world transforms after the animation has run, and you will only pay the same cost for the animation update, because that will be a batch update. But if the script moves something or you do something special like that, then you will get the update immediately. So I'm thinking that is the better choice, actually, rather than doing this lazy update. And that is also the method that we were going for in the new entity system. We will do the updates immediately and have a special path for these batch updates when we have one system that wants to set a bunch of local transforms at once. So the scene graph, like most of our other systems in the engine, uses a data-oriented design. And what we mean by that is that we try to design the code so that the data is laid out in a good way in memory and we can walk over it linearly in memory. So so this is a graph, but we don't represent it as a graph. We don't have like a ton of pointers individually allocated. Like in a character with 100 nodes, we don't have 100 individually allocated heap objects with pointers between them that we have to go and chase around and really destroy performance. Instead, we represent that graph in a flat array. So we have a flat array that contains all the nodes in the graph, just laid out flat in memory. And the nodes here, as I said, they have a local position, a world position, and a parent index. And then we have, have the next node. It has a local transform, world transform, and a parent, and so on. So, and the parent here, the parent value, that's just an index into this array, or -1 if it doesn't have a parent, if it's a root node. But otherwise, it's just an index to another object in this array. So that's how we form the graph. It's all laid out. It's all laid out in a flat array, and the pointers, our pointers are in fact just indices, like these parent indices into this array. And we also have a dirty flag, like a bit mask with a dirty flag for each node to know if the local transform is dirty or not. And and these are also sorted so that the parent always comes before the children in the array. So these parent links always link to something earlier in the array. And that means that it's already ordered in the update order. It's laid out linearly in memory. So when we do the transform, we just walk over all these nodes linearly in memory. And we check the dirty flag. If it's dirty, we compute a new world transform. And if it's dirty, or if its parent is dirty, because the parent might be dirty, and then we need to transform anyway. It could be, we need to transform if our local position is dirty or if our parent's world position is dirty. So we just walk this array in order and apply those transforms. So very cache efficient, very localized, not the need pointer chasing or anything. These dirty flags, we actually keep track of these dirty flags and export them too. So when we do this update and look at the modified world transforms, we save a dirty flag for all the world transforms that we modified, because then we know that these world transforms are also the ones that we need to be sending to the render thread, so that the render thread can update its world transform. Because I said way back in an earlier talk, we have the render thread, which has its own sort of reflected copy of the world state, which keeps track of the world transforms of all objects for drawing. And that's how this is how we keep track of which objects we need to send on the queue to mirror to the render thread, so the render thread can update its position. So I think it's interesting to say something more about how we're handling moving objects, because this is one of the sort of key optimizations in the engine. So, as I've said before, it's one of the general principles in the engine, performance-wise, is that you should only pay the performance cost of things that you actually do. So the work we do for handling moving objects, which is things like doing transforms, reflecting to the render thread, all that stuff, the work we do should be proportional to the number of moving objects, because that's the objects that we need to do something for. It should not be proportional to the total number of objects we have in the scene. So it should be possible to have 1 million objects in the scene, and if just 10 of them move, our cost for handling that should just be 10. It should not be 1 million. So that's like our general principle, and also I think since we're doing a generalized engine, we don't want to lock down people into any particular use cases or any particular workflows. We don't really know what our users are going to do with the engine. So some people might want to create these huge static scenes with just a few moving objects, and then we want to make that possible. So the key optimization in making this possible is to keep a list, basically, of the moving units. So we need to make sure, so we have a list of just the moving units, so we don't have to loop through all the units in the scene in order to act on them, or even to check if they're moving. Because just looping over 1 million things and doing a check, are you moving or not? I mean, once you get up to 1 million static objects, that gets pretty expensive. So we want to break them out, these things that are moving, into a separate list. And this is like a general optimization that you see a lot in data-oriented design. You take the things that you want to that you need to process on, and you make sure you have a special list of just them, so you don't have to loop over everything. So in order to, we will need to insert and remove objects quite frequently from this list, because units start moving and stop moving all the time. So we want to make sure that both insertion and removal is order 1. And we've done that by letting the units actually keep track of their position in this list. So the units know their position in this list, which means that they can easily remove themselves from the list. They just do a swap arrays with their own position and the last position in the last unit in the array. And adding is simple. Of course, you just push back the unit to the end of the array. And of course, we need to do some bookkeeping to make sure we update this index when we swap units for the swap arrays, so that the unit always knows its current position. And then we update this list through some mechanism. So if someone from gameplay code, from Lua or C gameplay code, changes the position of a unit, or if the unit has an animation state machine, gets animated, we add the unit to one of these arrays. We actually have several of these to keep track of different kinds of moving units. So if this happens, we add the unit to the moving keyframed array that keeps track of all our animated or keyframed units that are moving. If we get a notification from physics, I showed you in the previous talk how we process events that happens in the physics world, and one of the events that we react to is when an object awakes. If you remember the concept of being sleeping and awake in physics, awake is when an object is sort of activated and it's moving about, and then once it comes to rest, then it will start sleeping. So we know that only the objects that are awake will ever move in the physics world. So we listen to those events, and when we detect that an object has awakened in the physics world, we add the unit to an array that we call moving dynamic, that keeps track of all the physics objects that are moving. To remove objects from these arrays, we have a different mechanism, because there is no falling asleep event in physics. At least I don't think there is. There used to be, but I think they removed that event. And also when from the script, when we have the script changing position, we know when the script changes position, because the script will say, set the position of this unit to this. But we have no idea when the script might stop changing position. Like, we don't know if whatever the gameplay code might decide, oh no, I'm going to stop moving this unit. But we don't require the gameplay code to send us a message and say, oh, actually, I'm not going to move around this unit anymore, because that would be kind of cumbersome for the script to keep track of. So instead of having events for removing objects, we have kind of a garbage collection system, or similar to garbage collection system, in that we scan a number of units in these arrays every frame. So I don't remember what the number is set to, but every frame we scan a certain number of units and we check them. So for the physics objects, we check, are these still moving? Are these still awake? Because we can ask physics that. And if they aren't still awake, if they've fallen asleep, we remove them from the array. For the script objects, when we add the unit to the array here, we actually set a timer, and that says like, well, this unit was moving in this frame. And when we do the check here, we check, well, has the unit moved in the last 5 frames? And if the script hasn't moved the unit in the last 5 frames, then we remove the unit from the moving array. So this sort of a pruning mechanism that will keep this list down when units stop moving. And we don't check the complete array every frame, because there could be a lot of units in this array and we want to be efficient. So we don't have to, it doesn't matter if a unit lingers around for a couple of frames in this array, as long as it gets trimmed eventually, so the arrays don't grow indefinitely. So this is a recent balanced mechanism for doing that. And only units that are in these arrays will have their scene graphs updated. So that's how we do this, only in the order of the number of moving objects, not in the number of total objects in the scene. And we do the scene graph update in parallel too. So we will do that through the job system. So when we're ready to do this scene graph transform, we go wide and do it on all units in parallel. So for linked units linked to other units, then we need to transform the parent units first, so that we have the world position of the parent's unit. Only then can we compute the transforms of the child units. And of course, if there might be a chain, like there might be an ammo clip unit attached to a gun unit attached to a player unit. So there might be an arbitrary long chain of linked units, and they must be updated in order for the final unit to get its right transform. So in a typical scene graph evaluation, you would do this sequentially, like start with the base unit, update that, and then the next one, and then the next one. But then we lose kind of the parallelism, and we kind of want to keep some of that parallelism because it's really good for performance to be able to do this in parallel. So we have a system for that. And the key there is to sort the units by link depth. So we start by computing the link depth of all the units. And by link depth, I mean the number of all the linked units. So by link depth, I mean the number of parents. So if I have a parent, but my parent doesn't have a parent, I have a link depth of 1. If my parent has a parent, I have a link depth of 2, and so on. And then we sort the units by this link depth. And we begin by transforming all moving units, like all of these moving keyframed in parallel. And that means that all the units that doesn't have any parent will have the right transform, because they don't have to take the parent into account. Then we do all the level 1 linked units. So that's all the units that just have one parent. Now we know that all the units that have no parent, they already have the right transform. So all these units' parents, they don't have any parent, because if these units' parents had parents, then they would be at level 2 and not at level 1. So we know that all the parents of all these units already have the right world transform, which means that we can do this transform in parallel for all these units that are linked at level 1. All the units have, all their parents have the right transform, and after this transform, all the level 1 units will have the right world transform. And then we can go on to level 2 linked units, so the units linked to these units, and we know that these units have the right transform, which means that we can compute the transforms of these units in parallel. So this way, by sort of dividing it up by level, we can still do the transform in parallel, just one level at a time. And we could continue here and do like level 3 linked units, level 4 linked units, but at some point we're going to hit like diminishing returns, because there's not going to be, the link depth is usually only that deep, so it's not going to be like a ton of units that are linked at level 4. So at some point it's better just to stop doing things in parallel and just process the rest of the units sequentially in order of link depth, of course, so that they will still get the update in the right order, but we won't attempt to do it in parallel. Currently we stop here at level 2. So if you're making a game with our engine where most units are linked at level 3, that would be kind of a weird game, but maybe everything takes place on a spaceship and everything is linked to something else on that spaceship, and so everything ends up at level 3, then you would get pretty crappy performance, because you would skip all these parallel stages and go into, everything would be done in this sequential phase. It would be a really odd case, but that's something that that could happen theoretically. So the world update, that's kind of interesting. What happens when you update the engine? And it's a world that takes care of that. And this sort of goes through the whole update from the application down into the world. So we have a loop in an application, which is sort of our main driving class for the engine. And we have an update call there that gets called every frame. So the application update gets called. It ticks the application timer through the time step policy that I talked about previously, and the real world clock. It does some other updates here too, like update the input system is called from here, the profiler is updated, like various updates, but I'm not that concerned about that now. I want to talk about like the units and scene graphs and transforms and what happens with them. But just so you know, there are a bunch of other system updates that happen here in the application update. But eventually the application calls out to Lua or the C gameplay code, if you have C gameplay code, and calls the update function in Lua, actually. So there's a base callback in Lua that is just called update. And it takes the delta time and the total application time, I think. So that's sort of the root entry point into Lua from the engine. Lua in turn, as I said, Lua is in control of updating the worlds. So Lua will call update for one or more game worlds where action is taking place. And then we're into the engine code, into the world update function. And the world update function starts by ticking the timer of the world. So the world has its own separate timer that gets updated with sort of the delta here that's passed down all the way from Lua into the world. And then it updates the animation state machines. So changing states, transitioning from one state to another, handling events in the animation state machine, all that stuff gets taken care of. Then it updates the playing animations. As I talked about in the animation talk, it advances the time of all the animations and samples them. So it gets the local position, the pose from all the currently running animations. And this state machine update may start new animation. If you get a jump event and you transition into a jump animation, the jump animation start playing and so on. And the state machine also controls the time of these playing animations, like if some of them should play back at a higher speed or something, that's controlled by the state machine. So that goes into this playing animation update. So the playing animation system update, we get back animated poses from all our animation. Then we update the animation blends. So the animation blends, if you remember, take a bunch of different poses for one character and blend them together into one final pose for that character. So it might be a crossfade between a running animation and a jumping animation, and perhaps some overlay animation on top of that. All of that put together into a single pose for the character. And then the result of that is written into the local positions of all the bones in the character. Then we go into this thing I talked about earlier. We compute the link depth of all the units to handle this linked update algorithm. Then we update the scene graphs. We do the transforms for the moving keyframe units, the moving dynamic units, and then the linked units, as I showed above. So at this point, we've applied the animations, we've done all the animations, and we've done all the transforms. So we have all the world positions from the animations. Next step is to do the physics update. So we need to do the animation first, because the animation drives the keyframed objects, and keyframed objects can be mirrored into the physics and push physics things around. So we need the animation update, get the keyframed objects update, and get that into physics. So next step is that we mirror kinematic colliders or keyframed colliders. We mirror those positions into the physics engine. So from the scene graph of the units, where we have the animation positions, we take those, put them into the physics system so that the keyframed objects would have the right positions in the physics. Then we do this thing, we apply wind and other continuous forces, or some other forces that we have support for that can be applied through the physics system. So we calculate the wind using the vector language that I talked about before, this vector field system. Calculate the wind and apply the wind effects on all awake physics objects. And then we run the physics simulation, and the physics simulation will do simulate all the dynamic physics object in the world. Next step is we separate overlapping movers. If for some reason two movers have come into contact with each other and are overlapping, we have a phase for separating them up so that they don't run into each other. Then we get the physics positions. So these dynamic objects in the physics, like rolling balls, things falling and stuff like that, those positions might have changed as a result of simulating physics. So we need to take those positions from physics and write them back into the scene graph. And then we may also need to update linked positions again, because we might have units that are linked to dynamic physics objects. So you could have a rolling ball, and then you have a sword stuck into the ball, so that's linked to that with unit linking. So we actually have a separate list of units that are linked to dynamic units that we keep track of, just as with this moving keyframe and moving dynamic list with these explicit updates. We keep track of this the same way, so that we can update just those things. So we get the physics positions, write them into the scene graph. So we now have correct scene graph with updated world position from both animation and physics. Then we do this reflection that I talked about, mirror the positions over to the render thread. Then we do this, we check for sleeping stuff, like can we move stuff off of these lists of moving units, as I talked about, this sort of garbage collection phase. And finally, we process events from animation and physics. Like, did we get any collision events? Did we get any trigger events from the animations and so on? So yeah, that's basically it. And as you can see, I talked a bit earlier in the threading talk that it would be kind of nice to sort of delay the results, not do this thing where we go wide and then go narrow immediately afterwards to collect the results. It would be nice if we could delay things a bit, but as you see in this main update, everything is sort of feeding into the next stage. The state machine controls the animation. We need the animation pose to compute the blends. This could potentially be done in parallel, I think, because the link depth doesn't change by this. But then we need the blends to update to get the transforms, to update the scene graphs. We need the scene graphs to mirror them into the physics. Applying wind maybe could be done in parallel. But we need these positions and the wind in order to simulate the physics. And then we need the physics stuff in order to mirror that back into the scene graph. And then we need those things to mirror into the render thread. So there's small opportunities for increased parallelization here, but a lot of it is locked in, where one step depends completely on the previous step in this sort of sequence. So yeah, take some thinking to think about if we want to increase the parallelism of this, how to do that. But also the serial parts here aren't that big compared to the parallel parts. Maybe it doesn't really matter. things to think about. I mentioned briefly about unit data. That's a system we have for storing small pieces of data inside a unit. And it allows you to store data in sort of a JSON-like structure. You can store, we support bools and strings and numbers and maps of things and maps inside other maps. And we don't have arrays, we actually only have maps, but the keys in the maps can either be integers or hashed strings. So you can sort of look up with a string or with, and if you use a string for lookup, you will use the hash of that string as an integer. So it's kind of the same thing. And the reason we're doing this is that this is only intended for really small amounts of data and not really big arrays or something. So we don't do actual hash lookups for the map here. We just loop over all the keys until we find some matching key. So it's pretty efficient, since we store this in a single memory block, so there is no pointer chasing. So it's just walking over a small amount of memory, comparing the keys. So as long as the number of entries in a map is not crazy, as long as it's like below 50 or something like that, this is actually pretty performant, even though we don't have any acceleration structure at all. We just go through it linearly and compare. But it's intended for small amounts of data and stored in a single memory block for efficiency. And the idea behind this system was to be able to store arbitrary gameplay data in a unit, so that when you place the unit inside a level, you could configure it a bit. You could say like, well, this unit should have a health of 100, or this unit should give you a score of 50 if you capture it, or whatever. And you can control this in the level editor and the unit editor. You can sort of set up these fields and configure them. You can also control them at runtime, so you could keep track, instead of keeping track of the health of a unit in Lua, you could keep track of it in this data. Just update it from Lua, but let the data be stored in this unit data. And at runtime, you can also store arbitrary Lua objects in this data. You can't do that from the editor, because in the editor, these runtime objects in Lua don't really exist, because we don't have the runtime of the game running yet. But at runtime, you could store arbitrary Lua objects. You could link a unit to sort of a Lua representation of that unit, or your class that simulates that unit in Lua. Now, what we've seen here, like over time, is that this system has been kind of abused to storing not only script data, but storing things like that are really system data. Like at one point we had like reflection probes represented at unit, and then they had some special script data specifying that they were a reflection probe. And then there was a scanning phase, would scan the world and find these special units and put them into systems and stuff like that. And there were multiple things doing that. We did that with navigation too, special units as markers for navigation and so on. And it's kind of, that's part of the reason why we're moving to entities, to get rid of this sort of people just hacking this system to get it to represent various kinds of things. I mean, it's not a bad hack as hacks go. It works, but it's not the best system either, because it gets kind of expensive when you had to start looping over all the units in the world, looking for special patterns of this unit data. The world and the level also support blocks of these kinds of data, so you can keep track of things in the world, like player score or whatever, in the same way. Unit references, I want to say some things about. Now, in most things in our engine, for most things we use hard references. So by hard references, I mean that you explicitly create an object, you create the physics actor, and you explicitly destroy it. You say, now I destroy this physics actor. And there's a clear ownership. Someone owns something. So the application owns the world owns the units, and the units owns the actor. So it's a clear chain of ownership. And when you destroy the application, it destroys the worlds destroys the units, and the units destroys the actors. And mostly we prefer this kind of strong ownership and explicit creation to sort of garbage collection and reference counting, because it's clearer. It's clearer who owns what. It's clearer when something gets destroyed. It's clearer how long something will live for, how long its memory will live, how long it might be referencing something else, and so on. But there are some exceptions to this. Not to ownership, really. We pretty much have clear ownership of almost everything. But there are some exceptions where we use weak references instead of strong references. So weak references are basically just references that can be invalidated. With hard references, like a regular pointer, if the object has been destroyed, you will get an access violation when you try to use it. But with these weak references, you will be able to ask, well, is this object still alive? And if it's not, you can avoid manipulating it. So that's the difference. So the exceptions to this is that in some systems, we keep track of things by ID. So for example, playing sounds, playing animations, playing particle effects. When you play them, you get back an ID, like an integer, which is an ID identifying this particular thing. And that ID acts as a weak reference that you can use to check, well, is this sound still playing? Is this particle effect still alive? And of course, the main reason for this is that these things will die by themselves. Like when the sound runs out or when the particle effect runs out, these things will die out. And if you had a hard reference, you would immediately get a crash. There would be no good way of keeping to referencing these things. So it's a good case for weak references. But we also use weak references to units. So we have a unit reference system where you can sort of detect if the unit is still alive or not. And this is quite useful from gameplay code because units may die for all kinds of reasons. They may get killed by someone or unspawn for some other reason. And by having a weak reference system, the script doesn't have to be notified all the time when this happens. Instead, the script can just check, well, is this unit still alive? Can I still use this reference? So the way this system works is that we have the unit reference is 32 bits. And the main reason it is 32 bits is that we want to store it in Lua as light user data. And on 32-bit systems, a light user data in Lua, a light user data is mainly intended to store a raw pointer. So it fits the pointer width of your system. So on a 32-bit system, you only have 32 bits of light user data. So that's why we use 32 bits for our unit references. So we divided those 32 bits up like this. We have 22 bits of index, 8 generation bits, and 2 marker bits. And I'll explain what all this means. The index is an index to a lookup slot in an array. So we have an array of all unit pointers we have in the system, and all units we have in the system, and the index points to one instance of those. So this means that we can only support 2 to the power of 22 units because we can't create more references than that. We only have 22 bits here. So that's around 4 million units. That's a hard limit in the engine right now. The generation is used to distinguish, because we have these fixed slots of 4 million units, but when we have a reference pointing to a particular slot here, say that this index has 10, so we point to the 10 slot. Now if that unit dies, we of course will put a null pointer into that slot, but at a later point we may create a new unit in that slot because we want to reuse these slots. Because if we didn't reuse the slots, we could only support 4 million units over the complete lifetime of the game, which is too restrictive. We want to be able to create and destroy lots of units. I mean, the game might be running for days. So we want to reuse these slots. And that's what we use the generation for. So the generation is just an index stored in every slot, and each time we store a new unit in one of these slots, we increase the generation number. So in this case here, a reference would say, well, we're at index 10 and generation 0, because it's the first unit that has been created in this slot. And if the unit dies and a new unit gets created in the same slot, in the slot then it would say generation 1. So when we checked if this unit was alive, we would check the index and said, oh, we're going to look at slot 10, and what's the generation number in that slot? Oh, that generation number doesn't match our generation number. Then that thing represents a new unit, which means our unit, the unit that this weak reference is referencing, has died. So then we will say, no, this unit is not alive anymore. It has actually died. So if you think about this, you will see that we can get into a wraparound case eventually. Like if we keep creating lots and lots of units, filling up these 4 million slots, and we do it lots and lots of times, so we go through each 256 generations in a slot, we might eventually get into a situation where you have a reference to an old unit that has died, but because the generation number in the slot that you reference has wrapped around, you will actually think that the new unit in that slot refers to your old unit that has died. We have quite a lot of headroom here with 4 million units and 256 generations in each slot, so I don't think that anyone has ever run into that in practice, but there's a theoretical limit here. These two marker bits here, they are used just to distinguish the unit reference from other light user data. Because we use light user data, I'll talk about Lua in a future talk, but we use Lua light user data for a lot of things. And they are just raw pointers. They don't have any type information or anything at all. So we want to store unit references in here, but we need to mark somehow that these unit references aren't actually raw pointers, because then we would confuse them with the other raw pointers that we want to use light user data for. So we do that by observing that we always allocate things on a 4-byte boundary. And that means that all our pointers that we ever use in the engine will have 0, 0 in the last 2 bits. And that means we can sort of utilize that in order to mark our unit references and distinguish them from pointers. So we mark our unit reference by storing 0, 1 in the last 2 bits instead of 0, 0. And by doing that, we can just check when we get light user data from Lua, we can check, well, what's the pattern in the last 2 bits? If it's 0, 1, then we know, oh, this is a unit reference, it's not an actual pointer. But if it's 0, 0, we know, oh, it's an actual pointer. And the reason we use 2 bits for this instead of just 1 bit, which would be enough to distinguish between pointers and unit references, is that we use the same kind of scheme for entity references too, which we'll see when I come to the entity talk. So the marker here will actually say 0, 0 for pointers, 0, 1 for units, 1, 0 for entities, and then we have 1, 1 left for some future extension if we want to continue this nice scheme with something else in the future. But one interesting thing to notice is that, well, we're kind of spending a lot of effort here trying to pack this thing into 32 bits. If we had a little bit more headroom here, we wouldn't have to worry so much about generation number wrapping around or having a total limit on the number of units we can then support in the game and so on. So it would be nice to have a few more bits here. And actually, once we are 64-bit only, we could change this to a 64-bit structure and have plenty of more room. So currently, I think we're 64-bit on all platforms except Windows. We still support 32-bit Windows because there are a lot of people who like to run XP still or other kinds of 32-bit window platforms. So we will eventually, at some point in time, we will phase out the 32-bit support completely. I'm kind of itching to do that, but since there's still a customer base around, they probably can't do it for another year or so, I don't know. At some point we should phase it out. And then we'll have plenty of more room here, and we won't have to worry at all about generation wrapping around or a maximum number of units, which would be kind of nice. So, 2 final points here. I see we're already over time. So I'll go through them a bit quickly. So levels. A level in the engine is a collection of units that can be spawned into a world. So you edit it in the level editor, you start a level, you put a bunch of units in, you save it down, and then later you can spawn that into the game world, and you'll get all those units spawned into the world. So an easy thing to think of a level is just as a collection of units. But it also has some other stuff in there. It has things like light, it has flow support, which I'm going to talk about future talk, particles, nav meshes, stories, entities. So there's a bit, it's not just, it's mostly units, but there's a bit more other stuff there too. And you edit in the editor, as I said, and you can spawn multiple levels into the same world. So you can, a level is just a collection of units, and you can have multiple of those and spawn them into the same world. And that's also how you might want to do a streaming solution. You could have the same world, and as you walk up to a door, you could spawn a new level behind that door, and then open the door and unspawn the level that you came from once the door has closed and behind you. So that's one way you could implement the streaming system with the engine. The level also has some special objects that we haven't talked about before. We've talked about lights and particles and nav meshes, and not in detail on some of these, but we've mentioned them at least. But there are some more special level objects that I thought I should quickly mention too. We have support for prototypes, and that's for sketching out a level, like white boxing a level. Just create white boxes, not for sort of a sketch of what the geometry of the level would look like, not the final geometry. And we compile those into a single static unit. So that's sort of a custom unit for that level that only exists in the level and not anywhere else. But that's what happens. It becomes a single unit in the level. We also have spline support. So you can draw splines in the level editor, and then you can query them, like what are the splines in this level? Can you give me some points of these splines? And I think these splines are a really weird thing to have as a general object. I think this kind of shows the drawback of not having proper entity and component support from the start, because this is something that some customer at some point asked for. We really need support for splines in the engine, and it's like, oh yeah, let's add splines to the level. But it's something that some games would need, and some games don't care about at all. It's kind of weird to have it as a first-class object in our engine. It makes much more sense to have support for splines as a plugin. Yeah, if you want splines, well, here's a plugin. You can add splines. If you want something else like point clouds or Bezier surfaces, or I mean, it's just random that it was splines that this customer wanted and not point clouds or Bezier surfaces or parabolas or whatever other thing someone might have wanted support for in the engine. So I think this is something that if we did it today, it would definitely be done through the plugin system and through the entity system. So there will be a spline component as a plugin that you could work with this thing. And the same kind of applies to another thing that we have in the levels called volumes. Volumes are just shapes. You can draw convex 2D shapes and sort of extract them to a particular height. And then you can query these shapes and query, like, is the player inside any of these volumes I created right now? And then you can use that to sort of drive lights, maybe drive events in the level, drive sounds and so on. But again, this is such a specialized thing. Like, why is it 2D volumes like this? Why isn't it like a 3D convex object? Or why isn't it spheres of influence or whatever. You can think of so many different things. So it's really something that should be an extension rather than a core concept. Another thing we have is soundscapes. That's a system for playing sounds, placing sounds in the level that start playing when the player gets close to those sounds. So that's sort of a system for ambient sounds in the level, like sizzling from torches, waterfalls, stuff like that. Again, something would be perfect as a plugin, but was created before we had the plugin system. We also have a scatter system, which I will talk a bit more below. That's the final point here. One issue with levels that comes up a bit is that spawning a level can cause a stall. So a level is a container for units. It can contain a lot of units. It can be like thousands or tens of thousands of units inside a level. And if you're trying to do this kind of streaming solution where you walk around and you go through a door and you spawn a level behind that door, that can create an issue, because creating 10,000 units takes a chunk of time. Now, the resource loading happens in the background, as I said in an earlier talk, so we can stream in all the resources of the level in the background. So we're not stalling because we're accessing disk. We're stalling just because going through this list of 10,000 things and spawning them takes a chunk of time. So I think this is something we probably want to look at some point in the future, like having a staged spawn of the level where it's spawned over a couple of frames or something similar to that, in order to avoid this big stall that can happen when a lot of things are spawned at the same time. So the scatter system, finally, the scatter system is a system that is used to populate the world with lots of small units. So the regular units in the level, they exist all the time. They're spawned when you spawn the level, and then they exist until you unload the level. And that's good for big things like chairs and houses and cars and stuff. But there's also a need for small stuff to sort of decorate the level, like vegetation, like small bushes and grass and trash on the ground maybe. And if we spawned all that stuff as units, the engine would become really slow. It would really tank the engine down. And also it's just a memory just to store a lot of data for all these units. So the scatter system allows us to store just the position and rotation for each of these things. And as the user gets close enough, it will spawn a real unit and blend it in. So the representation looks something like this. Yeah, we have a scatter brush that spawns some specific unit. It has a distance where it should spawn, a distance where it should unspawn. They are usually different because you don't want it to pop in and out immediately. So you have usually a greater unspawn distance than the spawn distance. A method in which it should fade in. So it could either pop in, like immediately spawn. It could slide in on the Z axis, so it could sort of slide up out of the ground, which can look nice for some meditation stuff. Or it can scale in, like it can fade up in scale. And some range for controlling this fade, and then some pool settings for handling the pool, the number of units of this type that can exist. So the way this works is again an example of this, of thinking a bit about like the cost and not spending cost on stuff that doesn't matter. Because the simplest way to do this would be to every frame we go through all of these units and check the distance to the player, and if they're close enough we spawn real units. But once you have like millions of these things, which you might want to have if we're talking about grass things, that becomes really, really expensive. So what we do instead is that we sort sort these things in buckets based on the distance to the player and sort of geometrically scaled. So we have units, one bucket with units that are at least twice the spawn distance from the player. Then another one that's units that are 4 times the distance from the player, 8 times the distance from the player, and so on. And we check a certain number of units every frame, but based on how far the player has moved. So in this closest bucket, we check the distance the player has moved divided by sort of the spawn range. And this means that once the player has moved the entire spawn range, right, like a distance x, we will have gone through all the items in this bucket, because we check proportionally with how much we have moved. And that means that once we've moved a distance x, which means that these are a distance 2x away. So once we've moved a distance that would bring these close enough to be spawned, we will actually have checked all of them. And the same applies to all these others. We check the ones that are further away, we check them less often, and the ones even further away less often, so that the time we spend checking is proportional to the distance the player has moved. And we can't actually move fast enough. If we move faster, we'll check more things, so that we will actually have checked everything to move into a closer bucket by the time we get close enough to those things. So that maybe doesn't make complete sense, that explanation. But the point of it is that by dividing it in this way by the distance to the player and reducing the frequency of checks, we sort of keep us from checking, because each of these buckets will contain more and more objects, but we will check fewer and fewer of them, because it will take more and more time before we can move the distance to get close enough to these objects where they would pop in. So we can afford to check them with less frequency. That's the main idea behind the algorithm. And we don't have to go into the details of it. So that's basically it. All the things I wanted to cover for today. Do you have any questions? All right. Thank you, and we'll talk again tomorrow.